Okay, welcome back, everyone. So today's yet another continuation video from obviously the first two videos, where we essentially, again, as a recap, in the first video we talked about, the basics of differential equations, the essential terminology to continue, and the second video we set up a basic groundwork for how we compute linear ODEs of first order. So today we're going to be doing two good examples, one a bit more tricky than the other, but both fairly simple. So this first example we have here is fairly basic. So obviously the first step that we have to consider is converting this differential equation into standard form. Let me just convert this to zero occupancy so that, yeah, we don't deal with this strange, yeah, okay. So how would we do that? Well, in order to do that, recall from the previous video that we need the coefficient of the dy dx term to be 1, and the coefficient of the y term to be a function of x, and the right hand side to be a function of x as well. And notice that dividing both sides by x gives us that standard form. So and I'm going to write this as y prime since it's quicker to write. So what we have after dividing by x gives us y prime plus 6 over x y equals x squared minus 1, right? So now recall that the second goal here is to find our integrating factor, which from, as you might recall from the previous video, the integrating factor is defined as mu of x equals e to the integral of f of x. Well, it's not a definition. We proved this in the previous video. Yeah, e to the integral of f of x dx, where recall that f of x is the coefficient of the y term here. So in other words, in this case, we're integrating 6 over x. Okay, notice that by integrating both sides by x, this is a subtle note, but x cannot be 0. So later, we're going to kind of find an interval definition for this, and that'll be useful for us. Okay, well, how do we continue? So, well, if we integrate this function, this is a very basic integral. It's just going to be 6 times, that's a long 6, 6 times the natural log of the absolute value of x. Don't forget this absolute value. And recall from previous argument that we don't need the c plus c here. We're only going to end up with one constant of integration later on. Okay, well, notice that by log properties, we can bring this 6 into here, or we can just consider as this 6 raising everything to the 6th power and then eliminate the ln and the e, but I like doing it like this. So this is equal to ln absolute value of x to the 6th. Okay, so in other words, this is just going to be, well, let's see. It's just going to be cancel the ln and the e. It's just absolute value of x to the 6th. But notice that, well, notice that this inside term is always non-negative. In fact, it's positive because we can't let x be 0, as stated here. So this, we can kind of just eliminate the absolute value sign without any worry. So that's just x to the 6th. In this case, of course. All right. Well, let's see. So now, obviously, our next goal, maybe not so obviously, but from the previous video, our goal is to multiply both sides of the standard form here by x to the 6th. So when we do that, we get x to the 6th y prime plus 6x to the 5th y equals, what do we get here? That's just going to be x to the 8th minus x to the 7th, or sorry, x to the 6th. Okay, that's nice. So, well, notice that from the previous video, we note that this left-hand side is always going to be the product of y times mu of x prime. So the derivative of this product. And just to see that in this case, well, notice that our first term here is x to the 6 and y prime. Then we have 6x to the 5th y. So here we first take the derivative of y and leave the second function the same, and then take the derivative of this first function and then leave the second function the same. So in other words, we can easily see that this is just the derivative of the product x to the 6th y. So that's equal to x to the 8th minus x to the 6th. But notice that when we integrate both sides, again using a part of the fundamental theorem of calculus, derivative is the antiderivative is the opposite of the derivative, or the integral. So we just get x to the 6th y equals, well, this is a basic integration. We have 1 over 9 x to the 9th minus 1 over 7 x to the 7th plus c. Okay, well, now that tells us that y and our final goal is just going to be 1/9 x to the 3rd minus 1/7 x, just x, right, plus c over x to the 6th. Okay, now there's also something called transient terms, and those are terms where so we have three terms here, right? Transient terms are terms where if we take the limit as x goes to infinity, then that term is equivalent to 0. And notice that the only transient term here is c over x to the 6th, since c is just a constant and x to the 6th keeps going on to infinity, so that goes to 0. So this is our transient term. And now for the interval of definition, well, this has no restrictions except for x can't be equal to 0, as seen over here, and obviously this x to the 6th in the denominator. So we can either choose the interval of definition of 0 to negative infinity to 0 union. So that's our interval of well, it's not our interval of definition yet. It's just when this is defined. But our interval of definition takes the largest one. So, well, we saw this in the previous video again. Actually, in the video before the previous video. But we can take either of these since, in a sense, they have the same cardinality. That's kind of, that can be, that's not necessarily true. You can kind of get iffy with infinity again. But we're just going to choose any of them, and I'll just choose this one. Okay, cool. Well, that's this problem finished. So now let's go into a bit of a trickier example. The only reason it's trickier is because it deals with, these annoying, theta value, trigonometric functions. As long as you know the derivatives of trigonometric functions, we're fine here. And possibly even definitely even the integrals of them too. But usually I might just rederive them, so it's not a very big deal. Notice that this is already in standard form. And the reason things might get, you might get a bit confused here, one might get a bit confused here, is that, well, this time we're dealing in the coordinate system r and theta. So it's kind of like the transformation from, r and theta. So it's basically you can think of this as the transformation x equals r cosine theta, and then y equals r sine theta. Okay, so it actually might be possible to I'm not sure if it's possible to actually convert, but that's just what this is. So we're dealing in the r theta plane here. So polar coordinates. Let's see. In this case, we can think of our y variable, it's happening again, whoops. I guess I have to decrease the occupancy again. So we can think of our y variable as r in this case, right? And then so that's our dependent variable. Our independent variable is going to be theta. So in other words, we can see that this is already in standard form, since we have this side as a function of our independent variable and our r variable, which is the dependent variable, times some function of the independent variable. So we have our desired form already. So now let's just find mu of theta in this case, I should say. So mu of theta is e to the integral, well, secant of secant theta. So this is what I mean about computing integrals of trigonometric functions. Now secant theta, it's one of the more trickier integrals to memorize, but you don't even have to memorize it. Well, honestly, if you know how to like the general method for computing it, you should have already have it memorized, because I'll just share that here, but it's really beautiful. If we consider the integral, if we hone in on this integral, we can multiply. So think of this as the fraction secant theta over 1. We can multiply the top and bottom by secant theta plus tangent theta. So over, this is just 1, so this doesn't cause any harm to the integral. But notice how beautiful this is. Because what we get here, if we distribute this, the numerator is just going to be secant squared theta plus secant theta tangent theta. I'll just omit the theta just to be a bit concise here. But so secant plus tangent. But notice that if we let u be the denominator, it's exactly, if we take the derivative, so like du is just going to be, what is the derivative of secant theta? It's just secant tangent theta plus, and then plus what is the derivative of tangent? Well, that's just secant squared. So it exactly matches the derivative, it exactly matches the numerator. So in other words, this is just going to cancel out. You can think of that if we solve for theta. D theta, I should say. So in other words, this integral just becomes the integral of 1 over u, which is just ln of the absolute value of u. But what is u? U is secant theta plus tangent theta. So let's just finally evaluate this. This is e to the ln of absolute value of secant theta. Sorry if I went a bit quick through that. But it should be pretty well known if you're in differential equations. And I think this explanation suffices for now. Okay, well, oh yeah, and tell me if you want me to make a series on integration techniques and things like that. Anyway, again, we can cancel this. They are inverse functions. And then we're just left with the absolute value of secant theta plus tangent theta. Okay, so now here's where we get, here's where things get maybe a bit complicated. But since we're just wanting to find one interval of definition, one of the intervals of definition, we can just omit the absolute value. But when we omit the absolute value, we want to see when this function is greater than 0. It can't be equal to 0 because this function goes into the natural log function, and the natural log of 0 is not defined. So we want to find when this function is greater than 0. Secant theta plus tangent theta is greater than 0. But how do we do that? Well, let's return to monkey. But instead of monkey, we're returning to the original, sine and cosine. So we have one, sorry for that. I don't know what that was. So it's 1 over cosine plus sine over cosine. So it's 1 plus sine, if we combine them. 1 plus sine theta over cosine theta. But when is this greater than 0? Well, an important note is that sine theta ranges from negative 1 to, so the range of sine theta is just negative 1 to 1, right? If we don't have any scaling factors next to the sine. So the amplitude is just 1. But notice that it's 1 plus this. So in other words, well, in this case, sine can't be equal to negative 1, otherwise this would be 0. So in other words, this function, since we're assuming that it's not 0, it's always going to be positive, right? If sine is not negative 1, it's always going to be positive. But notice that that just tells us that we want to find whenever cosine is positive. So when cosine is positive, well, if we look at the unit circle, cosine is the x value on the unit circle. So, well, let's see. So it's just going to be, we want to find this half of the circle. It's just going to be this where the x value is positive. So this just tells us that theta can range from negative pi over 2 to pi over 2, right? So that's where our theta is defined. And to perhaps be more rigorous, we would say, well, we would have to include like all possibilities, perhaps. So like it would range from negative pi over 2. And notice that we have open brackets here because the denominator can't be 0. Negative pi over 2 plus 2 pi a, and then pi over 2 plus 2 pi b. Okay, where a and b are integers. Okay. But usually on an exam, it would just ask you to find, like one of these intervals. So we can simply just take negative pi over 2 to pi over 2. But just for the sake of rigor, perhaps, we can keep this entire interval. So this will actually be our interval of definition. And again, well, I guess the interval of definition would just be if you chose 1. I'm not 100% sure, but it might depend. It probably depends on what class you're in, but usually I guess you would just take one of these, so negative pi over 2 to pi over 2 would suffice. Okay, so now let's actually continue with the problem and multiply both sides by secant theta plus tangent theta, right? We took the positive possibility. Okay, so when we multiply both sides by that, well, this might look a bit messy, but we're going to have secant theta plus tangent theta times dr d theta plus r secant squared. This is a similar case for when we dealt with the actual integral. We saw that if we multiply secant theta by secant plus tangent, we get exactly this term here. And multiply that side by secant theta, we just get, well, secant or secant plus tangent. Cosine is, well, secant is 1 over cosine, so we're just going to get 1 plus, well, sine, because tangent theta times cosine is just, tangent is sine over cosine, so the cosines cancel. Oh, and we're just left with sine. But notice that this is just going to be the derivative of the product of, well, here we're taking the derivative of r first times this mu the derivative of mu of theta, right? Because this is, again, this is the same case with the integral, but secant squared is the derivative of tangent, and secant and tangent secant is the derivative of secant. So it's just going to be secant theta plus tangent theta prime equals this. Okay. Okay, so when we integrate both sides, we just get r times secant theta plus tangent theta equals 1, when we integrate this, well, it's just another basic integration. It's just going to be theta minus cosine theta plus c. And solving for r, we finally get the following. We get theta minus cosine theta plus c over secant theta plus tangent theta. And this solution does not have any transient terms, because whenever we let theta vary, whenever we let theta go to infinity, well, these are, cosine and sine. Well, in this case, we're dealing, cosine and sine are wave functions, so they don't approach a singular value at infinity. And furthermore, tangent has an asymptote at pi over 2, so it's the same idea with it being like periodic after 0 to pi over 2, after that it begins its cycle again, goes from negative infinity to positive infinity. So yeah, it doesn't make sense in this case. So there are no transient terms. And we already dealt with the interval definition. So that is about it. I hope you enjoyed this video and I hope you found it helpful. And yeah, have a nice day and goodbye.